Section 7.14, the chelates and macrocyclic effects. The chelated complexes are much more stable than their non-chelated analogs. This is the so-called chelate effect. Essentially, the chelate effect is the entropic effect. In the formation of a chelated complex, the entropy of the system increases significantly. So now let's look at one of the chelated complexes. Right here, EDTA forms 4 bonds with this iron transition metal center. It does look like a crab using its claws to catch this iron. And supposedly this 2 nitrogen can also form 2 bonds with the transition metal center. That will further increase the chelate effect. Here's another example. This is simpler. The ligand is 1,2-diaminoethane. Now this bidentate ligand can also form 2 bonds with this transition metal simultaneously. The arrows indicate that these 2 bonds are donor-acceptor bonds. So really, this nitrogen used 2 lone pair electrons to form the bond here, and this nitrogen also uses 2 lone pair electrons to form the bond. So this transition metal does not share its own electrons with the ligand. Really, these 4 bonding electrons come from the ligand only. Now let's talk about the entropic effect. Let's compare 2 reactions. In this reaction, this hexaquacadmium reacts with 2 ammonia molecules and form this diamine tetraaquacadmium plus 2 water solvent molecules. In this reaction, we replace the 2 ammonia molecules with 1 EN molecule. EN is diaminoethane. It's a bidentate ligand. It can replace 2 water molecules. This is the product plus 2 solvent water molecules. So they really look similar to each other. In both cases, 2 cadmium oxygen bonds are replaced with 2 cadmium nitrogen bonds. So supposedly the energetic effects are similar in these 2 reactions. And it is indeed the case. So if you just look at the enthalpy of reaction, they are very close to each other. However, if you look at the entropy of the reaction, these 2 differ significantly. So one is 25, the other is 113. In the chelated reaction, the entropy increase is much more significant. And why is that? Well, my trick is just to count the number of molecules and ions in the liquid phase. We compare the left-hand side and the right-hand side. So over here, if you look at the left-hand side of the reaction, there are 3 molecules or ions. So you can say 3 particles. And over here, you have also 3 particles. So really, they cancel. Now look at this reaction. In this reaction, on the reactant side, you have 2 particles. On the right-hand side, you have 3 particles. There is 1 more particle in the liquid phase that can move around. So that means there's a more significant entropy increase in this reaction. So again, you just need to count the number of molecules or ions on the left-hand side and on the right-hand side. When a chelated complex is formed, you observe an increasing number of molecules or ions in the liquid phase. So now let's say if we have just 1 EDTA ligand with 4- charges, it can form 6 bonds with a transition metal center. So that means if you have, let's say, hexaqua ion reacts with EDTA, it's possible for this EDTA to swap out all 6 aqua ligands. So on the left-hand side, you have just, one EDTA here. On the right-hand side, you will have 6 water molecules that can move around much more freely. So that means you observe a increasing number of molecules or ions that can move more freely in the liquid phase. That results in the increase of the entropy of the system. So now let's get back to this case. In the formation of the chelated complex, the entropy increase is much greater than its non-chelated analog. We can just analyze this entropic effect quantitatively by using e to the power of, this is the difference between the entropy of reaction for these 2 reactions divided by R. The result is nearly 40,000. So due to the entropic effect, this reaction is much more favored by a factor of nearly 40,000. Now let's talk about the macrocyclic effect. So you're looking at a very large ring here. When a transition metal forms a complex with this kind of macrocyclic ligand, indeed there's also very significant entropic effect. But in addition to that, there's also energetic effect. This is favored energetically as well due to the pre-organized nature of the ligating groups. So you have this groups here. Once you put a transition metal here, you're forming 1, 2, 3, 4 bonds easily with this 4 points of attachment. Okay, these 4 nitrogens are just too far away from the center. Okay, from the center. So these 4 nitrogen atoms cannot form a bond with the transition metal center. And also, I just want to remind you, this nitrogen has a lone pair, but this lone pair electrons are right here, not here. It's right here, 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 here. They are just far away from the transition metal center. So only these 4 nitrogen atoms can form a bond with the transition metal, assuming the transition metal fits properly here in the center. So if the transition metal is too large or too small, then that will lower the formation constant. Sometimes you see a very large formation constant, as large as 10 to the power of 12 or even 10 to the power of 25. So such a large formation constant is a sign of the chelate effect or the macrocyclic effect. Chelating may also affect the kinetics of the complexation favorably. This is because when one ligating group is bonded to the metal, or other ligating groups can bind to the metal easily and quickly. So let's imagine this case. Okay, this is 1,2-diaminoethane. Once this nitrogen is bonded to this transition metal, and this NH2 functional group supposedly is very close to this metal as well. And this formation of a second bond will be quicker than between this metal and another free ammonia molecule. Same here. Now imagine this crab is your EDTA, and this crab has, you have to imagine there are 4 claws here. 1, 2, 3, 4. 4 acetato ligands. Once one of them is bonded to this ion transition metal center, the other 3 will be really close to this ion and can form the bonds quickly and easily. But again, I want to remind you, very likely these 2 nitrogen atoms can also be bonded to this ion to form a octahedral complex. It's just because I'm using this crab to illustrate the chelate effect. So from this picture, it's not clear that these two nitrogen atoms can also be close enough to this transition metal center and also form two bonds.